Hello students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss about Newton rings. This is a topic concerned with wave optics lesson, and here we are going to see how the theory of Newton's rings goes, and we will develop some formulas for bright and dark fringes, how the Newton's rings are formed with the interference of two waves by reflection method. Here we will see some introduction before going to the actual theory. So these rings are of equal thickness, an example of equal thickness. So Newton's rings are considered as an example of equal thickness. So how the equal thickness is formed when the rings are formed? You can see actually the rings are like this. They are formed around a central dark spot, and there will be a consecutive bright dark, like that. The fringes are circular. So the theory behind this was first observed by Newton when he was doing some experiments on light passing through different mediums. When it was passing through different mediums, he was observed that it has a pattern of rings when light was passing through some films, like thin film like air or glass or some liquid thin films. So he has observed the pattern, and he was continuously doing some research work on how to understand this Newton's rings pattern. So here we have an experimental arrangement which can produce Newton's rings by considering thin film in the thin film interference. In the previous lesson, I have discussed how the waves will be interfering in thin films. What is a thin film? It is an optical medium of very small thickness. So you can go through my previous video if you want to understand the interference pattern in thin films. Now we have an experimental setup here. This is a glass plate. This is a plano-convex lens of large radius of curvature. You know what is the radius of curvature? This curve, if extended as a circle, we have a center here, that is called center of curvature. The distance from the center to the circumference of the curve is called radius of curvature. So this is an air film between the plano-convex lens and the glass plate. The air film is of variable thickness. You can see the air film of variable thickness. The thickness at the central spot, if you consider this as O, this thickness is almost negligible, almost zero. So it will increase while we are going to the left or right. So this is a plano-convex lens, and a glass plate is introduced between the plano-convex lens, and there is a microscope here where we can observe the interference pattern after reflecting from this air film. So this is a sodium vapor lamp, the light source, and this is a lens which creates the parallel rays which are falling on the glass plate, which is put at an angle of 45 degrees inclination to the x-axis. So when these rays are coming from the source, sodium vapor lamp, these incident rays are incidenting on the convex lens, then the parallel rays from the lens are incidenting on this glass plate. So when they incident on the glass plate, some of the percentage of light will be refracted and some of the percentage of light will be reflected. So the refracted rays will go like this, but we have not seen in this diagram. Only reflected rays from this glass plate can be seen, and when they incident on the convex lens, they are passing through the convex lens and they will be incidenting on the air film here, which is of variable thickness. So the reflection happens from the two borders. So the air film is, see, this is surrounded by a glass plate and a plano convex lens, right? So the two borders are of glass. So in between there is an air thin film. So the light rays will be reflected from the above surface of the thin film, and they are also reflected from the below surface of the thin film. Okay. In this way, the reflection of waves takes place, and they will be having some phase difference while reflecting, and the two rays which are moving in the same direction after reflection from the thin film, so they will form an interference pattern based on their optical path difference. So the optical path difference will give the phase difference. Based on the phase difference, we can understand whether it is a constructive interference or destructive interference. So if it is a constructive interference, we will see a bright ring. If it is a destructive interference, so we can see a dark ring. So the rings pattern can be observed through this traveling microscope here, exactly put above the convex lens. So to view the reflected rays, the rings pattern you can view with microscope. We cannot see the rings pattern with the naked eye. Why? Because they are of very small wavelength. We know. So see, they are of from monochromatic source. They will come from monochromatic source, and this monochromatic means of single wavelength. So it is having the two rays is refracted from this lens, and they are having a parallel beam. So we need two coherent sources to actually form an interference pattern. So these two sources will act as two coherent sources. Okay. Now we will see the condition for the bright and dark fringes. What is the condition for dark and bright fringes? So from our previous class, we know the optical path difference. When the light is passing through the thin film, we have calculated as 2 mu t cos r minus lambda by 2. This is the optical path difference. Okay. When this optical path difference is equal to some, say, the condition for forming a bright fringe is the optical path difference must be an integral multiple of lambda. Okay, this is the condition for bright fringe. Okay, see here, mu is refractive index of air. We can take it as 1 t, the thickness of the air film, or see here the incidence of the light wave from here, this glass plate, is normal to the medium. So we can take it as normal incidence. This is a normal incidence method, and when it is incidenting normally, the R is equal to angle of refraction is 0. So this cos R will become cos 0 is equal to 1. So we can write this equation as 2 t minus lambda by 2 is equal to m lambda. So mu becomes 1. We have t as thickness of the air film, and r is 0 degrees. So cos r becomes 1, and minus lambda. This is the correction what we have done in our previous class. A correction is made for a reflected wave. When it is reflecting from a medium, it will undergo a path difference of lambda by 2. So we have a correction like a lambda by 2 here. So here the 2t will become m lambda plus lambda by 2. Okay. So if you take the lambda by 2 outside, this will become, okay, see here if you multiply this one with this, we will get this one. So here the condition for the bright fringe will be 2t is equal to lambda by 2. So if the thickness is multiple of this lambda by 2, this is odd integral multiples of lambda by 2, then a bright fringe is formed. So in the same way, we can get the condition for dark fringe. What is the condition for dark fringe? The optical path difference will be same. Here we can write this condition for dark fringe will be the optical path difference must be equal to odd integral multiples of half wavelength. So in the same way, this 2t minus lambda by 2 will become 2m plus 1 to lambda by 2. So when you take this lambda by 2 to this side, what happens? Okay, see here, if you can take the lambda by 2 outside, so this will become 2m plus 1 plus 1. Okay, so this will become 2 into lambda by 2 into 2 into m. So this will finally, we can write it as 2t is equal to m lambda. Okay, so in this way we can get the condition for bright and dark fringes. Okay, so we have the condition for dark and bright fringes. So in this way we will understand how the dark and bright fringes are formed comparing with the thickness of air film. Okay, now we see what is the radius or radii of dark fringes. Radii of dark fringes, or we can also take it as for bright fringes, anything is same. So how to get the radii of dark fringes means, see the same setup, experimental setup, I will briefly introduce in a way of geometrical way, in which we can calculate the radii with some triangular properties. So if I suppose at a point Q a dark fringe is formed like this, and see here I will take this point as P, and see here, okay, this is the thickness of the air film. T is the thickness of the air film, and this distance from this point, I will say this as N, suppose this as R. Okay, this is the radius of the dark fringe. Suppose if at Q a dark fringe is formed, the Rm is the radius of the dark fringe, and this is the radius of curvature. You can take it as small r as radius of curvature, or you can take it as capital R as radius of curvature, give it this another name as M. Okay, if this is radius of curvature, this is also radius of curvature, right? So what happens is, see, when the dark ring is supposed to be formed at Q, the radius of curvature will become this from this center O to Q. That will be written as Rm. Rm is the radius of curvature. So how to get this Rm means, if you can understand the diagram like MNP, the triangle MNP, from MNP what we can write by Pythagoras theorem, R square is equal to Pn square plus MP square. So r square is equal to, what is Pn square? Rm, radius of the dark fringe, plus mp. This distance, how can we get this distance? This is the radius of curvature, that is r, and this distance is the thickness of the air film. So mp can be taken as r minus t whole square. Okay, so in this way we can write this equation like this. So here, if you can understand what is radius of curvature is, the radius of curvature is far greater than the thickness of the air film. Radius of curvature is far greater than the thickness of the air film, because we have taken the convex lens of very large radius of curvature. So by this, with this we can write r square is equal to rm square plus, these terms, r square, minus 2rt plus t square. Okay, with this what I can write? If these terms are observed, so 2rt is far greater than t square. So we can write here rm square is nearly equal to 2rt. Rm square, r square is cancelled here, and we can neglect t square because 2rt is much higher than the t square. So this rm square is nearly equal to 2rt. So from this what we can write is rm is equal to root of 2rt. Okay, so for a dark fringe, what is the thickness? Previously we have derived what is thickness for a dark fringe. It is m lambda. As from 2t, if you take m lambda, so this will become r m lambda. Okay, in place of 2t I have written m lambda. So with radius we can calculate the diameter of mth ring, that is radius is always double, diameter is always double the radius, so we can take it as rm. Okay, in this way 2 into rm is nothing but rm lambda. Okay, so from this formula we can calculate the radius of curvature of a given plano convex lens. How we will see, if you square it on both sides, this will become 4 rm lambda. Okay, so what is r? We can take it r as dm square by 4m lambda. The radius of curvature of a given plano convex lens can be calculated by this formula. Okay, now we see what is the spacing between the fringes, the dark fringes. So we have calculated the diameter of the dark fringe as this one. We can get the dark fringe diameter. How the dark fringe has some spacing in between them. That means every fringe has some spacing between them, right? That is called fringe spacing. So how to calculate the, observe the fringe spacing means, so here we know dm is 2rm, that means 2 into root of rm lambda. Okay, if you take the first order, that means 2 into m lambda, first order means you need to take r lambda, where m becomes 1. So this is 2 into r lambda. If you take, then m becomes 1 here. The second order dark fringe diameter will become 2 into root of this m becomes 2 lambda. Though in this case, what is root 2 value? 1.4 nearly. It becomes r lambda. Okay. If you calculate the diameter of third dark fringe from this formula, say here the m will become 3, then it will goes like as, what is root 3 value? Nearly 1.7 we can take into r lambda. So if you observe the diameter here from first, second, third, so this will be changing. The diameter is changing, and it is changing, and you can observe the diameter how it is changing. So with this observation, we can say the diameter will be the spacing between the fringes as you move from the central dark spot away from the spot left or right. The fringes will be having some spacing which is narrowing while we are moving away from the dark spot. So they will have a very small fringe space when you are going far away, like d4, d5, d6, d7, like that. Okay. So what about the equal thickness of fringes? We understood now the fringe spacing will decrease when you are moving to the higher order fringes. What about the thickness of the fringes? So all the fringes are of equal thickness. That's what the Newton's rings are all about. All the fringes are of equal thickness. So why? Because see, every fringe is having its locus around this plano-convex lens. Suppose, see, a fringe is forming at this point. See, the thickness of the air film is same at this point. So around this plano-convex lens, all the locus of these points which are having the same thickness of the air film, they will form a bright or dark fringe depending on the phase difference. So if they are having the same thickness and a ring is formed exactly connecting all the locus of these points around this plano-convex lens, then the thickness of the fringe will be same. All the fringes are of equal thickness. That is the logic behind the equal thickness of all the fringes, and they will form the circular fringes also. Once they are of equal thickness, see, the shape of the ring will be circular. Why? Because if you take all the these locus of all the points which are having the equal thickness around this plano-convex lens, they will form a circular ring. See, if this is having some thickness, and at this point if you take another point, this is having some thickness which is lesser than this point. So if you connect all the points which are having the thickness here as of same thickness, they form all the locus of the points will form the circle around plano-convex lens. So in their way, the fringes are of same thickness and are also fringes are circular. Fringes are circular. Okay, these 2 points we must remember when you are understanding the theory of Newton's rings. So in the theory, we are coming to a conclusion, right, where the central spot, which is having almost a negligible thickness here, will form a dark spot. So either it can form a bright spot or it can form a dark spot. Why it is having a dark spot? because see, when the air the light waves are coming and touching this plano convex lens, and they are passing and they are touching here, suppose exactly at the center where the lens is touching the glass plate and the thickness is almost negligible. So what happens is, here the thickness is almost negligible, means the optical path difference lambda by 2, optical path difference is lambda by 2. So here the t will almost be 0. So then the optical path difference will nearly equal to lambda by 2. That means when a light ray is incidenting here, it will reflect. While reflecting, it will undergo a path difference of lambda by 2, or a phase difference of 180 degrees or pi radians. Okay, so when the incidenting light ray and the reflecting light ray is having a phase difference of pi radians, they will be forming the destructive interference pattern. See how we will see. This is a plano convex lens, and see the waves which are forming here, they will be like this. Once they are reaching here, and the light incidenting this plane, some part will be reflected back, and again the reflection will takes place at this point, the 0 point, where here it is. So if you observe these two reflected rays, they are moving in the same direction, but they are having a phase difference of pi radians. That means they have a crust to trough correspondence. So once the phase difference is like this, they will form the destructive interference. That means the redistribution of light is having a zero intensity. We know the interference pattern is all about redistribution of light. The light energy will be same, but it will be distributed as the high intensity and low intensity. The high intensity areas are bright fringes, the low intensity areas are dark fringes. So here the pi radians phase difference will make these waves interfere destructively, and there is a central dark spot is formed at the 0 spot where the lens is touching with the glass plate. So this is the theory of Newton's rings, and I hope you understood this theory and concept well. In the next session, we will see actually the experimental pattern of Newton's rings, and we also calculate the radius of curvature of a given plano convex lens by using the experimental arrangement. Okay, thank you.